Yes, so what is an ODE? An ODE is an equation of this form: f x y dy dx d square y dx square, so on till dn y dxn equal to 0. So here x is the independent variable, and y is the dependent variable. Now to solve an ODE, of order n, we need n conditions. Example, y of 0, okay. Okay, so once you have n conditions, you can solve for the an ordinary differential equation. Now there are two types of ODEs. This is two types of problems. One is the initial value problem. Okay, it's a problem where only initial conditions are given. So y of 0, dy by dx at 0, and so on. There's something called a boundary value problem. Okay, where some conditions are not given at the initial value of x. So example could be, you could be given y at x equals, I don't know, just making something 5, but then everything else could be at 0. But it could also be that more than one condition could be given at non-zero. So that's a boundary value problem. Always IVP are easier to solve than PVP. Okay, always, because it's easy to initialize and then go forward, march in. Let's say x was time, then it's easy if you just want to march forward with values at 0, but going reverse when you're given something at some time, 5 or something, makes it a little hard. So that's one thing. The other thing is that sometimes you'll be given, or many times you'll have like a equation of nth order. And the way to solve the nth order equation is to break it into first order equations. What I mean by that is, so to solve ODEs, reduce n order or nth order equation into n first order equations. And I'll give you an example so it becomes clear. So for example, if you have an equation like this, dy dx d square y dx square, so on till dn yn dny dxn equals 0, then you would write it as y0 is y. You'll create new variables. These are just creating new variables, y1, y2. Yeah, so we keep doing that till we end up with yn, which is dn y dxn. Okay, so we have introduced n new variables here, y0, y1, y2, so on. Okay, the reason why we want to do this is because this step helps us to write n first order equations. So that would be dy0 dx. So if you take the derivative of y0 with respect to x, that's dy dx is nothing but y1. Then d square y1, sorry, my bad, should be dy1 dx. So derivative of y1 with respect to x is d square y dx square. But d square y dx square is y2. So that's y2. And just keep doing that till dy n dx would be sum fx y0 y1 y n minus 1. Okay, there's an assumption in this. We assume that the original equation was something like this. So what we did here was we substitute this as y0, this as y1, y2, and so on till yn minus 1. And that's what is written here. Okay, so this is these are n first order equations. It's weird. Yeah, and I'll give you an example. So it's not like this might be hard to see without a specific example. So I'll give you an example. Okay, so here's a solution. So first of all, we'll write the highest order equation, which is d cube y dx square, as minus 2 d square y dx square minus y minus x square. Okay, once we do that, now we introduce variables y0, y1. So y0 will be y. We just do it. y0 is y. y1 would be dy dx. y2 will be d square y dx square. y3 will be d cube y dx cube. So that's the first step. We've introduced these new variables, which will help us to write the first order equations. Now we can do dy0 dx. So derivative of y0 dy dx is nothing but y1. D square y1, sorry, my bad again, dy1 dx. So derivative of y1 with respect to x is basically the second derivative of y, but the second derivative of y is y2. And similarly, dy, you know what, let me just write this as steps so it's easier for you to understand. Y1, 2, okay, dy3, sorry, dy2 dx is d cube y dx y3, right? Because that's y3, and then dy3 dx. Wait, what am I doing? That's not right. It shouldn't be 4 equations. It shouldn't be 4 equations. They're just third order. So I shouldn't have this, right? So it should be d. This is d cubed, so it should be minus 2 d square y dx square minus y minus x square. The last one can be rewritten as d y2 dx equals minus 2. What's d square y dx? So it's y2. What's y? It's y0. And then x is x squared. That's my third equation. It basically comes from this one. So those are my equations. This will be first, second, third. 2, 3. So 1, 2, 3 are the required equations. Okay. Okay. So consider the ODE. dy dx equals f of x comma y. The initial condition is y of x0 is y0. Okay, so that's a problem. Like, for example, if you're told dv dt is a, okay, v is velocity, a is acceleration. If you know the acceleration, you can then compute v by integrating this equation, right? So that's an example of what we're going to do. Now, the reason why we do want a numerical method is, what if a was something very complex? It's like sines, cosine, exponential. It's just not possible for you to integrate that analytically. And that's why we are trying to go for a numerical method. So a is possibly complex equation and difficult to integrate analytically. Okay, hence we need numerical solution. And that's true for all the 3 methods which I'm going to talk about. Okay, so what does Euler's method do? Well, it's just it's this way. So we choose x increment delta x. So you would choose how much you want to increment the x. This gives you grid points x0 plus I delta x, where I will go from 0, 1 to all the way to your chosen n. Okay, then for this equation, dy by dx is fxy. We can just use a finite difference scheme. By finite difference, I mean I replace the derivative with just 2-point difference, right? This is dy by dx. We've learned about the forward difference. This is just the forward difference equals f of xi yi. So note this is forward difference. We did this in the early part of this course. So now we can write yi plus 1 is yi plus delta x f of xi yi. Okay, so what is done here is we typically use the value of yi, the initial value. We know it's y0. We then compute what y1 is, right? Because everything on the right side is known. We know what f of xi yi is. We're given f. Delta x is assumed by us. Y0 is known. So y1 is found from that equation. Then once y1 is known, we find y2, y3, and y so on. So let me just write that down so that when you refer this, it's obvious. So you'll do y1 equals y0 plus delta x fx0 y0. Next, you'll compute y2 y1 plus delta x f of x1 y1, and so on till whatever time yn equals yn minus 1 plus delta x f of x n minus f of x n minus 1 yn minus 1. So the solution is basically what are the values at different x's. So you'll get at x0, x1, x2, so on till xn, you will get y0, y1, y2, so on till yn. So this is what you really wanted. You want to find what y is at a given x, right? So for example, for the acceleration example, you know what the initial velocity is, but you're given the acceleration. You know the velocity at v0, v1, v2, so on till vn. Okay, so now this is an approximation. The approximation here was based on finite difference, forward difference, right? So forward difference we know is only so accurate. So this solution has some problems with accuracy because it's based on an approximation. So what exactly is that approximation? Well, for that we need to look at the truncation error, and only for this one I'll derive it, but for the other ones I'll just give you the answer. So if you want to compute the truncation error, you just Taylor series expand yi plus 1, which is nothing but y xi plus delta x. It is y of x plus delta x d. This is a complete derivative because there's no two variables, plus delta x square d square y dx square plus so on. But phi of x is nothing but yi plus delta x. dy by dx is nothing but the f xi yi plus this, everything here is of the order of delta x square. So we see that the Eulers expression is accurate to delta x square. Okay, so it's accurate to delta x square. So clearly, to get good accuracy, you want to reduce delta x as much as possible because, for example, if you use delta x 0.1, your solution is accurate to 0.01. 0.1, then 0.01. If 0.01, then or 10 raised to negative 2, then it would be 10 raised to negative 4, and so on. So the truncation error is of the order of delta x square. Okay, so the total error, which you basically obtain by summing up across, you need to sum it across all the intervals, becomes truncation error times n. This is basically the summation, and that is actually equal to approximately delta x. So the total error is approximately delta x. Well, n is, put this, n would be your approximately proportional to 1 divided by delta x, right? Bigger the grid is basically the number of points, the smaller is delta x. So when you take delta x square divided by delta x, you get delta x. Okay, so this method is also an improvement over Euler's method. So it's also called improved Euler's method, or it's also called actually Runge-Kutta order 2. Okay, there's another name. Other people also discovered it, Runge-Kutta being one of them. Okay, so what's done here is there are two steps. This is one of the methods which falls in the category of, it's like a prediction correction type method, and I will get into this a little bit later in this chapter. So what it does is basically predicts a change what is this? This is just the Euler's method, right? Yi plus 1 is yi plus delta x f of xy. So that's the prediction step. This is what Euler will give you. This is same as Euler. But then there is a correction step which takes this value and improves the estimate. Plus delta x divided by 2, and it's the arithmetic mean of f of xi yi plus f of xi plus 1 y star I plus 1. So that this thing is showing up here. Yeah, so why delta x divided by 2, why this? That's the question, right? How did it appear? And it turns out that it all is somehow boils down to the Taylor series. You need to put this in the Taylor series and figure out why this particular assumption. It turns out that when you put it in Taylor series, yeah, question? Okay. If you put in the Taylor series, you'll see that the truncation error is actually much better than, is smaller than the truncation error of Euler's method. So I will not go through that derivation, but the truncation error of this method is approximately order delta x cube, just by assuming this special, whatever the equation is, that's the correction equation gives you that. Okay, and then total error is always one order higher, is proportional to delta x squared. So it gives you one order of increase in accuracy just by improving this doing this extra step. Okay, so now what we'll do is we'll see how to apply this on a problem, right? That's how we learn about how to use it. So here is a problem. Okay, so this is these calculations are kind of tedious like previous ones, but I think that by resorting to good practices in terms of how you write things down, you can make your life easy. So this, what I'm going to show you is one way of doing this calculation so that when you present your work in the exams, it's very clear what you're doing. But then there are other ways too. So what I do is this. So Eulers method. I know the formula. It's yi plus 1 is yi plus delta x f of xi yi. And then, so xi is going to be, remember, it's x0 plus I delta x. x0 is 0. This should be, well, I should be from 0, 1, 2, all the way. I think it should be up to 10, because when you do 10 times 0.1, you get 1. x0 is 0. So what I can do is I can just generate a table. xi 0, 1. Okay. 0, 0.1, 0.2. Just increase the spacing. 0. I'm going to run out of space. 0.1, 0.2, 0.3, 0.6. Yeah, I'm only going to go to 0.9, and it'll be clear why I'm doing that in just a bit. Okay, and then yi. Okay, so what I know about yi is that I know the value at x equals 0. It's 1. It's given here. Okay, so in order to do this, what I'll have to do is I need to go row-wise. So just to make my life easy, I actually write down everything I need, right? This part. And then I plus 1. So if I sum this one with this part, then I get yi plus 1, as I see in the formula. So I need to take a calculator and punch in delta x. Delta x is 0.1. I need to put the value of f. So y would be 1. So you can see that it's going to be delta x 0.1 times 3, because y is 1. So this will be minus 0.3. And then yi plus 1 is, since the sum of this row and this, so this column yi and delta x f of x comma y, this will be 0.7.
Delta x f of xi yi.
Yes, so it's maybe even easier. Delta x times f of x y is this. So minus 3y. So 3 by 3y, I mean 3yi. And so when you put it, you just put 0.1 because that's given. And then y is 1. So 0.1 times minus 3 is minus 0.3. Then you need to sum these two up by this formula, right? So sum is 0.7. Now take the 0.7. That's the new value. That's the value at the next time step, right? I plus 1. Again, compute delta x times 3y. Do that quickly. 0.1 times 3 times 0.7. I get 0.21. So negative 0.21. Then I sum the two up. .49. Then I move the 0.49 here. I compute that, and you just have to keep doing that. So it's kind of tedious, but you'll appreciate a calculator, or even Excel will do this, or Octave when we get to the part where we're coding it, right? So we just have to keep doing that. And I did this, well, I would say for the exam, you have to use the calculator, but for homework, just do it for 2-3 iterations and then use a code, and I'll give you code. I've actually also posted code for the last chapter. So I did this calculation. I'm just going to splash the whole thing in front of you, so you can do calculations by hand yourself and check with my answers. Yeah. This? Sure. Let me just write it here. It's this 0.1, 3 times yi, 0.7. This would be 0.1 minus 3, 1. Okay, so from my notes, okay, so I'll just keep it here. Just verify a few more, and so you get the hang of it. But I don't really expect you to copy this so quickly. So this will be in my notes. Let's go to the next part. So this question is asking you to compute the same one with Heuns or Heuns method. Let's do that. Yeah. -3 over here.
Yeah.
Can't be, right? So 0.7 times 3 times 0.1. 7 3s are 21. You check. So what's 0.7 times 3 times 0.1? 0.21. What's that?
Now I was asking you, where should get where you getting the -3 from?
-3, it's from here. It's -3y. I just put this here. Yeah, I just put, yeah, this value. And same for here. And then, yeah. Okay, correct. Okay, so let's sometime we can finish Heuns method. Heuns method is the next one. Exactly the same thing. Let's first establish the formula. So we have y star, y plus 1 is yi plus delta x, f of x, I, yi. Then we have yi plus 1 is yi plus delta x divided by 2, f of xi, yi plus f of xi plus 1, comma, yi plus 1 star. Okay, so ask yourself what you need here. You need xi, you need yi. You'll always have those. Then in order to compute yi plus 1, you probably need this term. Okay, I'll just call that dy star, and the star is because of the star there. So dy star Okay, then once I get dy star y, I'll be able to compute yi plus 1 star by just summing this and this, right? Next, yeah. It's just a temporary variable which goes in here. It's a prediction, and this is a correction. Okay, this is actually the same as Eulers. Yeah, so we actually can do this here. Instead of trying to figure out what's next, just put 0, 1, that's known, that's given. We can compute dy. It's going to be, again, 0.1 times minus 3 times y. So that would be minus 0.3. We need to sum them, 0.7. So we've reached this point here. Next, we need to compute this term, and I'll call that, let's call that just dy, no star, because that d by dy mean this whole thing. Hey, where of course you'll sub in the values when I say this is, by the way, what, minus 3y, right? And then this is minus 3yi, and this is minus 3y I plus 1 star, right? So then what we need is this dy. Here we can, this is like getting a kind of a harder calculation to do by hand, but we need that value. Once we have that value, we need to sum this value, this dy, with yi plus 1. So you sum this with this, and you'll get your new estimate, yi plus 1. So dy comes out to be 255. And then y plus 1 is yi plus dy, comes out to be 0.745. I can also write this one here. This one is yi plus dy star. So you can do this for the next one, 0.1. yi, you just carry forward this one here. We're almost out of time. 745. And then dy from that formula comes out to be 0.2235, 0.5215, minus 0.19, and 0.555. So you just keep doing that. So I just sort of broken it down into a column, so it's table, so you can typically debug this and find what the flaw is in case you've found an error. So I'm just going to not do it here. I'm just going to copy paste my solution, which I did offline. And then you need to probably go back and verify this. Copy.